Hello everyone, in this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to examine the uncertainty principle. Alright, we cannot give, at this point, a full derivation, but we can give a kind of hand-wavy semi-quantitative one, connecting the uncertainty principle to wave-particle duality. So imagine you're accelerating a beam of electrons with wave function psi at a narrow circular aperture. One can consider the uncertainty in the vertical position of the beam, to be related to the diameter of that circular aperture. So the uncertainty in the vertical position, in the sort of y-axis, if you will, is delta x, unfortunately named in this case, but delta x is about equal to b over 2. But as that aperture gets narrower and narrower, then when they go through, they diffract, and you get larger and larger wave behavior. So the more delta x is narrowed in, the more uncertainty in the momentum of those particular electrons you see. There is sort of their default or most likely momentum, that is straight ahead, but as they're bent by some amount delta p, or the uncertainty in the momentum itself. So if b is about equal to the wavelength that beam diffracts, and the wave nature becomes evident, and lambda measurable, and theta is about equal to lambda over b as a result. Notice I've dropped my factor of 1.22. This is pretty hand-wavy anyway. But theta is about equal to lambda over b. As a result, delta x, as a result, that uncertainty in the momentum over the momentum, is about equal to theta as well for small theta, is also about equal to lambda over b. Then we take that relationship and we cross-multiply here. And we observe that b is also about equal to the uncertainty in the position times 2. We substitute that in step 4 here. And finally, we divide by 2 to get the uncertainty in the momentum times the uncertainty in the position. And that gives us that the uncertainty in the momentum times the uncertainty in the position is about equal to lambda p over 2. But lambda, via the de Broglie hypothesis, is also equal to h over p. Our momenta cancels, and therefore the uncertainty in the momentum times the uncertainty in the position is about equal to h over 2. Now notice this is super approximate, but it gives them some sense as to how you might have sort of a trade-off here. Sort of the narrower the aperture, the larger the uncertainty in the momentum, the wider the aperture, and therefore the larger the uncertainty in the position, then the less uncertainty in the momentum you would have. Qualitatively, this is a decent way of going about it, but in truth, this relationship, that is the uncertainty principle, is fully derived using mathematics that are simply beyond the scope of the course.